So today I'd like to present my recent research, and the topic of my presentation is invariant representations of simplicial complexes. Okay, so first let's talk about our topic of interest, 3D objects. They are everywhere and found in many applications, such as characters in gaming and product design and the chemical industry also. So today's topic is about how to analyze these objects. To manipulate 3D objects on a computer, we often use triangle meshes. Just think of a triangle mesh as a collection of triangles connected together to form a 3D object. And mathematically, we can refer to this as a simplicial complex. I will talk about what a simplicial complex is later. So we want to do some interesting things with these 3D objects. And specifically, we want to do tasks like classifying, regression, and clustering, for example. Classifying means assigning label to each object based on their features, and regression is predicting a continuous value for an object, such as each size or each weight. And clustering is the process of grouping data together based on their similarities. So how can you do that? How can you extract useful features? To do these kinds of analysis, many people find it useful to first find a vector representation for each 3D object. So in this slide, we see a virtual example I made. And once we have these vector representations, that means each 3D object corresponds to a point in a Euclidean space. With these points, we can perform various tasks. So our goal is to find an appropriate representation for each 3D object that suits the given task. Yeah, so to obtain representations for 3D objects, there are various methods already that we can use. I will briefly explain some of the ideas, but we won't go into the details because we don't have that much time. The first method for representing a 3D object is to divide it into a regular grid of small cubes, and this is called voxel. And it is basically a 3D grid in Euclidean space that represents the object using many cubes. So after converting the data into voxel format, we can obtain a representation for example, using 3D convolutional neural network. And the second method is that if there is a 3D object in the middle, like here, then we can take many pictures from multiple directions, right? So we can analyze these pictures. There are already various techniques to analyze the images. So using that information, we can obtain a representation of a 3D object. The third method for representing a 3D object is to sample many points on a 3D object and then analyze these points. One popular approach is to make a graph using these points somehow, and then use a graph neural networks to obtain a representation. But I want our representation to have two types of invariance. The first one is isometry invariance. Okay, on this slide, we have 5 triangle meshes of rabbits. And in fact, these 5 data were made from one mesh data. I rotated and translated and mirrored sometimes to the mesh data to make these 5 mesh data. Right, so someone might say, actually, these 5 rabbits are the same rabbit. They are the same rabbit from different angles. Therefore, the representation vector for these objects should be the same. So we call this the isometry invariance of representation for 3D objects. That is, we hope that representation of a 3D object doesn't change even if you apply any isometric transform to it. Right, subdivision invariance is another type of invariance that I want our representation to have. When we talk about subdivision, it is the process of subdividing each simplex in a simplicial complex into similar or equal simplexes. So here we have 2 mesh data of rabbits again, and actually to create the one on the right, I subdivided each triangle in the left mesh into 4 triangles. Although they have different simplicial complex structures, but their appearance are completely the same, right? So some may argue that these 2 are actually the same because they have the same appearance. That is our second invariance, which means we hope that the representation of any simplicial complex remains unchanged even after we perform a subdivision on it. So in summary, what we want to do is to find the representation vector for each simplicial complex that fits a given task. And we also want this representation to have two desired properties, isometry invariance and subdivision invariance. Okay, so before discussing how to proceed, let's first go over some background for this topic, starting with the definition of a simplicial complex. Right, to define a simplicial complex, let's start by introducing simplices. A simplex in Rn is a complex whole of k+1 finely independent points. Since we will be focusing on 3D simplicial complexes only, so we only need to know up to 3D simplices below. Then we can now define a simplicial complex. A simplicial complex is a collection of simplices that satisfy certain conditions. And these two conditions can be thought of as rules for how to glue simplices together. So one reason for reminding this is to emphasize that I'm not dealing with abstract simplicial complexes. So because many studies often deal with abstract simplicial complexes, which are more abstract than these kind of geometric simplicial complexes, but the purpose of this presentation is to deal with simplicial complexes embedded in a specific R3 space. So I will only deal with these simplicial complexes defined in this slide. Right, another term we will be using frequently is this embedded simplicial complex. So when I defined a simplicial complex earlier, I said it was just a collection of simplices. And this embedded simplicial complex is simply the union of those simplices. To denote the embedded simplicial complex of a simplicial complex K, we typically use a different notation. But in this presentation, just for convenience of notation, we will use the same notation K. Right, on this slide, I will talk about notations again that I will use often. For an embedded simplicial complex K and an invertible matrix M, Mk denotes another embedded simplicial complex obtained by taking the inverse of M at every point in K. The reason I use M inverse here instead of M is just for convenience of notation, and you can see why in later slides. And also you can add a vector to a simplicial complex here. So it is basically a translated simplicial complex. Another notation we will use is related to pullback. So given a function f defined on Sn-1 and an orthogonal matrix R, R star f denotes another function defined on Sn-1, where given an input x, the output is frx. So this is basically a pullback induced from the orthogonal matrix R. Okay, this is the last slide for notations. I will introduce two more terms that frequently appear in this presentation. First, let's talk about invariance here. I think this invariance is a familiar term to many people here, and it means that something remains unchanged after a transformation. Here is an example. Let's say we have a function f and an operator p. And if this equation holds for every orthogonal matrix R here, then we say that P, the operator P, is O3 invariant because O3 transformation doesn't change the output of the operator P. And as the simplest O3 invariant operator, we can think of an operator that takes the maximum or that takes the average, because these values do not change even if the function f is rotated or flipped. And these maximum and average functionals can be implemented in neural networks, and those are called pooling or pooling layers. So they are called maximum pooling layer and average pooling layer. Okay, so next term is this equivariance. Actually, for me, this word was a little less familiar than invariance. And this equivariance refers to the property that when a transformation is applied to the input of an operator, the same transformation is also applied to the output in a consistent manner. Okay, let's look at an example again. Suppose we have a function f defined on S2 and an operator p that takes a function defined on S2 and outputs another function defined on S2 here. So if these, if the following equation holds for every orthogonal matrix R, then we say that this operator P is O3 equivariant, because if you see here, if you see this equation, the orthogonal matrix comes out of the operator P, right? That means this operator P is O3 equivariant. Right, now let me introduce the proposed approach in my recent research. Here is a simplified procedure for the proposed approach, which will be further explained in the following slides. First, let's say we have a simplicial complex K in R3, and then we are going to use an operator F here, defined on S2, where the output is again a function. So in other words, through this operator F, we obtain a function that gives us a curve for each point on the S2. So this notation map R to R denotes a set of functions mapping from R to R, and a function in here doesn't need to be continuous. Okay, so I'm going to give you a very quick overview here and then go into more detail in next slides. Before that, I'd like to highlight some properties of these operators that I will define later. First, the operator D and P have the following properties. So if you look at the first equation here, I put RK plus V as an input for the operator DF. The first note here is that on the right side, there is no V here, right? So the vector disappears on the right side. And this means that this operator DF is translation invariant, because the vector V can be thought of as a translation information of a simplicial complex. So it means that this operator DF is translation invariant. And second note here is that the orthogonal matrix R comes out of the operator DF, right? And that means this operator is O3 equivariant. And in the next line, if these two things are the same, I mean, if these two vectors are the same, then that means the operator P is O3 invariant. So if P is O3 invariant, then we can know that the vector PDFK here in our B space is invariant under the isometric transformation of a simplicial complex, because every isometric transformation can be decomposed into an O3 transformation and a translation. So we have a translation invariance here using this operator DF. And if we can get the O3 invariant using this operator P, then we can know that this vector PDFK in our B space is isometric invariant. Okay, so I will explain these properties in more detail in the following slides. First, I will discuss the operator F first, which is called Euler curve transform. And to understand this transformation, we first need to understand the Euler characteristic. So let's remind ourselves of the definition of the Euler characteristic. Given a simplicial complex K, the Euler characteristic is defined as the alternating sum of the number of simplices. And as we know, the Euler characteristic is also equal to the alternating sum of the ranks of each homology groups. Therefore, we know that the Euler characteristic of a simplicial complex is invariant under the subdivision of the complex. But in fact, this Euler characteristic can be defined in a larger class, the class of semialgebraic sets. Here I have written the definition of a semialgebraic set, and a semialgebraic set is a set defined in Euclidean space by finite unions and finite intersection of sets induced from these inequalities and zero sets of polynomials. Right, it may look complicated, but the typical examples of such a semialgebraic set is an embedded simplicial complex. As I mentioned earlier, a simplex is a convex hull of finitely independent points in Euclidean space. So each simplex can be made only using multilinear polynomials. So we know that each simplex is a semialgebraic set. And by the definition, since the class of semi-algebraic set is closed under union, so therefore simplicial complexes are semi-algebraic sets. As I mentioned earlier, the Euler characteristic is defined in a class of semi-algebraic sets. The following theorem states that every semi-algebraic set can be divided into a finite number of I cells here. A cell can be thought of as a kind of generalization of a simplex, which is, you can think it is a curved version of simplex. And using this cell decomposition, the Euler characteristic of a semi-algebraic set can be defined as the alternating sum of the number of I cells similarly. And one interesting property of this Euler characteristic is that it can be used to define an integration over semi-algebraic sets. First, to define an integration, we need this additivity property. And fortunately, we have this property for the Euler characteristic. And also, as not all functions are integrable, we need a certain class of functions, like measurable function in measure theory. Here we have the definition of constructible functions. And a constructible function is an integer valued function whose preimage under any integer is a semi-algebraic set. We will denote the set of bounded, compactly supported, and constructible functions on X as CFX. And then for all functions in CFX, we can define the Euler integral like this. So that is, the integral of f is a weighted sum of Euler characteristic over preimages. Yeah, so finally we can define the Euler curve transform. The Euler curve transform is an operator from CFRn to CFSM-1 product R space. So those are the spaces of functions. And the Euler curve transform, we can define the Euler curve transform as the Euler integral of the product of f and a characteristic function here. So this formula may look complicated at first, but since we are dealing with simplicial complexes, so we are going to use the characteristic function of an embedded simplicial complex K. So if we plug in the characteristic function in this formula here, then this formula becomes quite simple here. So in this case, the transform simply computes the Euler characteristic of the set KVR, where KVR is defined here. So it is an intersection between the embedded simplicial complex K and a half space defined by V and R. V is an element in Sm-1 and R is an element in R. So to illustrate what the set KVR is, so let's take a very simple example here. So let's say we have a very simple simplicial complex here, and here V is a direction. I mean, V is an element in Sm-1. So we have a direction V and we have a real number R here. So given V and R, we can define a half space like here in this region. And the intersection of this half space with the embedded simplicial complex K gives a portion of the complex here, which is darker region in this figure. So you can say that the Euler curve transform records the Euler characteristic of this region for every direction V and for every real number R. Right. So the most important theorem in this Euler curve transform is this injectivity. So that means this transform from CFRn to CFSM-1 product R space is injective. Without this injectivity, we cannot know that we can distinguish different two things after a transformation, but the Euler curve transform somehow preserves enough information to distinguish two different things. So yeah, it is a good thing. Therefore, instead of analyzing simplicial complex itself, it is sufficient to analyze this object, this function R1K. Because we are only interested in simplicial complexes, so let's simplify the notation. Let fk be a function defined on Sm-1. So for each point on Sm-1, we get an alpha function. I mean, we get a curve for each point on S2 as the following formula. Actually, this function is just another way of representing the Euler curve transform of the Simplicial complex K, because if you see here, if you see this formula, then this function records every Euler characteristic information for every direction V and for every real number R. Okay, so we will call the function, we will call the curve assigned to each direction by this function an Euler curve here. And thanks to the injectivity from the previous slide, if there are two different Simplicial complex, if there are two different embedded Simplicial complex K1 and K2, then the induced function, this fk1 and fk2, must be different. Yeah, so we have an example here to show what the Euler curve transform looks like. Suppose we have an elephant mesh data like here in the middle. Then for each direction, that is for each point on S2, the Euler curve is defined. Right, so another note here is that I think you can easily see that if we rotate the mesh data like this, then the result of the Euler curve transform will also be rotated in the same way, right? And moreover, if we translate the mesh data, then you can imagine that each Euler curve for each direction will also be translated. And we can formalize this as follows. Given a Simplicial complex K, if we apply an ordered transform and a translation to a Simplicial complex K, so in this case Rk plus W, then the resulting Euler curve transform can be expressed in this way. So it means if we transform K using an ordered transformation using R, then the Euler curve transform is also transformed in the same way, meaning it has an O3 equivariant property. And it is not translation equivariant, but we can observe that each Euler curve is translated if we translate the Simplicial complex K. So our objective was to get an invariant operator, translation-invariant operator, right? So how can we obtain a translation-invariant operator for a Simplicial complex? We can achieve this by applying translation-invariant operators to each Euler curve, because we only need to remove this W term in this formula, because this W can be thought of as the translation information of a Simplicial complex, so we only need to remove this term. And this can be formally stated as the following proposition. So if you have translation-invariant functionals on our 2R functions, and if you apply them to each Euler curve, then we get a translation-invariant function with respect to Simplicial complexes. And it is still O3 equivariant, and this subdivision invariance is quite straightforward because we are dealing with the Simplicial complex K using each characteristic function of an embedded Simplicial complex. Right, so then the next step is that how can we construct these translation-invariant functionals, DI, in this slide? How can we make it? A very simple translation-invariant functional that we can think of is the maximum functional. It is obvious that even if you translate an R2R function, the maximum value will remain the same, right? Well, we can also consider the minimum functional. However, these invariants contain too little information. So we can easily lose too much information that we may need for our given task. To obtain various translation-invariant operators, instead, I will apply many translation-equivariant operators first, and then apply a simple translation-invariant operator, such as this maximum functional. And this is possible for the following reasons. First, let's consider a translation operator TC here, which takes a function and gives a translated function. Also, let's assume that there are several translation equivalent operators, GI, and let's define H as the maximum functional. Then the composition of operators from H to G1 here will be our translation invariant operator. Right, so if you see these equations, you can know that since G's are translation equivalent operators, so we can keep moving TC forward one by one, like here. So And also, since the maximum functional h here is translation invariant functional, so TC disappears at the end. So what we can see from this is that the composition of these operators from H to G1 becomes a translation invariant operator. This means that we can obtain various translation invariant operators by making different GIs, different translation equivariant operators. So the next step is changed. So now, how can you make these GIs? How can you make these many translation equivariant operators? One of the most popular translation equivariant operators is this cross correlation operator. It is very similar to convolution, which many of you might be familiar with, but the sign is somewhat different. The cross correlation between these two functions, f and g, is defined by this integral. And its translation equivariance can be proved quite easily. That is, the cross correlation between TCF and G, TCF was just the translated function of f by c, is same as the translated function of this cross correlation between f and g. So using this operator, we can obtain various translation equivariant operators, because if we change the function g, then that means we can get a new translation equivariant operator. And actually, this operator is a continuous version of a convolutional neural network that is widely used in deep learning. Right, if we consider a one-dimensional convolutional neural network, I will just call it 1D CNN. We can think of it as having a filter that moves along the data and sequentially computes the output. I mean, the inner product between the filter and the data. And you can consider it as a discretization of the cross correlation we discussed earlier. So when we actually compute it on a computer, we will use this 1D CNN to approximate a translation equivariant operator. Okay, so let's summarize what we have discussed so far. First, given a simplicial complex K, we can use the Euler curve transform to obtain one Euler curve for each point on S2. And then we use many translation equivariant operators, and at the end, maximum functional to obtain this function dfk. This dfk has the following properties. It is invariant under translation, and it is equivariant under O3 transformation. However, in reality, we cannot handle these data perfectly on a computer. This is because first, there are infinitely many points on S2, and also each Euler curve itself is a function from R to R, so we also need to discretize it. Therefore, we need to choose finite points on S2 as uniformly as possible here, and calculate Euler curve only on those points. And also, we cannot directly handle the R functions, so we need to discretize the Euler curve using a predetermined resolution. Then we can obtain this function, dfk function, using the discretized Euler curves with CNNs, and at the end, the max pooling layer. Right, so now so far, we kind of achieved translational and subdivision invariance. So the only thing we need to do is to find an O3 invariant operator. As we did before, we will stack multiple O3 equivariant operators first, and then add a pooling layer, such as maximum pooling layer or average pooling layer. Therefore, we will make an operator T to approximate an O3 equivariant operator. And I will use a graph neural network, GNN for short, for this purpose. Okay, to use a GNN, we first need to make a graph, right? Because it is a graph neural network. So here is how we do it. First, we choose a suitable positive number R here, and we are going to sample quite uniform points on S2, and we will fix it after sampling once. And then we created an edge between two sampled points if the distance between them is less than R. And then we did a null feature for the GNN, right? And node feature means just the function from nodes of a graph to a Euclidean space. And we use the function dfk as the node features. Okay, so before I explain more about the GNN used here, let me show you how I sampled these points and how I created the graph. For generating the points, I used the subdivision of the icosahedron. Actually, there are several ways to uniformly sample points on a sphere, and one of them is to use the subdivision of the icosahedron. So if there is an icosahedron, we can subdivide each triangle of the icosahedron into smaller triangles, and then we can project them onto the sphere. And this method also naturally gives us the edge of our graph. So when I conducted experiments, I always use this method to generate a graph, but of course you can use other methods. Okay, now let me explain the GNN that I used. I used a graph convolutional network, which is GCN for short, which is one of the simple models in graph neural networks. What GCN does is updating the node features of a graph using its graph structure. To explain in more detail, let's say we have node feature f, which is just a vector for each node. Actually, there are various types of GCN, but one simple form of GCN is to multiply the neighborhood features of each node with this W theta matrix and take the average of them as a new node. So here is the formal equation here. Actually, in fact, when I conducted an experiment, I used slightly more complicated model, but it is okay to use it. So I will use this GCN in this presentation. Right, so let's get back to the main topic. We need to show the equivariance of this operator T. However, this expression doesn't make sense. So because if you look at this equation, R star F here is a function defined on R inverse X, because the domain of the function F is the set X. But the input function of T should be a function defined on X. So this expression doesn't make sense. So instead, what we can do is to naturally extend the domain of this function. We will create a new function called T prime, which is defined as follows. For each point x on S2, we calculate the average of W theta Fu, where U is a point whose distance from x is less than R, just like what we did when we constructed GCN. And then we can easily see that T prime F here is the same as the TF on the set X. Now, if we use T prime instead of T in this above equation, then we can now say that we want to show that these two things are similar. And this theorem can kind of guarantee that. What this theorem tells us is that for every positive number epsilon, the probability that these two values, actually these two vectors differ by more than epsilon, goes to 0 as the number of points we sample goes to infinity. So here n is the number of samples. So if they are the same, if these two vectors are the same, then that means T prime is O3 equivariant. So it means that if you uniformly sample a lot of points on S2, then the operator T prime can kind of approximate an O3 equivariant operator. And since T prime F and the TF are the same functions on the set X, so this theorem can be a theoretical background for using the GCN we defined before. So therefore, since the GCN layer we talked about can kind of approximate an O3 equivariant operator, so we can stack multiple GCN layers first, and at the end, a pooling layer to approximate an O3 invariant operator. Okay, let me summarize what we have discussed so far. First, we sample points as uniformly as possible on S2 here. And let's say we have a simple complex K. And then we construct this function fk using the Euler curve transform. Actually, this function was originally defined on S2, but we discretized the function. So we have this function from X to RD. Next, we use 1D CNN and a pooling layer to obtain this function, dfk. This function also was originally defined on S2, but we discretized, so we get this function from X to Rm. And I visualized the function dfk below using heat maps. And then we can use GCNs and at the end a pooling layer to construct this operator P. And this FC, that is the fully connected layer, is just for the visualization of an experiment. Actually, since we have already obtained the isometry invariance after these pooling layers, so it is okay to add any kind of operator afterwards. Right. So in this presentation, the proposed approach in this presentation involves several discretization processes. First, the Euler curve needs to be discretized with a predetermined resolution. And also we need to use CNN, right, instead of the cross-correlation. In addition, to achieve all three equivariant operators, the GCN was used. However, the related theorem that we saw earlier only holds when the number of points n goes to infinity. So we don't know how large the error will be, right, for a finite number of points. Moreover, discretization errors may accumulate as they are stacked in multiple layers. So to measure how much unintended errors can occur, so we conducted a simple experiment. Let me briefly explain the dataset used for the experiment. It is called ANIM or ANIM dataset, and I used 229 mesh data in this dataset. And there are 8 classes, including some animals like here, horses and camel, elephants, and faces, and so on. So the task I chose was to find a 2D vector representation for each mesh data so that the representation of each class is located at the vertices of the regular octagon in 2D space. For the training, I randomly selected 5 meshes for each class to train. Since there are 8 types of classes in the dataset, so I used a total of 40 mesh data without any data augmentation technique. During testing, I made these 3 new datasets, A, B, and C, by applying random isometric transformation to the entire dataset. And these 3 datasets were used as inputs to the model, and I observed the results. On this slide, we can see the model's output for each dataset A, B, and C. So here, there are 2 things to note here. First, the results for each dataset are quite similar, right? We randomly transform the data using random isometric transformation, but we have very similar results for the datasets. That means the discretization error is quite small. The second point to note here is that the model demonstrates quite a good generalization performance. The dataset is relatively simple, I think, but the model was able to effectively group each class using only about 20% of the training data. Okay, there's a lot of talk about details of what I've described here, but I will stop here and talk about things like future work or limitations. The first one is about the theoretical bounds of the error. When I used GCN, I mentioned that we couldn't determine how large the error would be for a finite number of points, right? Although we experimentally kind of verified that the error was small enough to use the model, but it would be great to have a theoretical upper bound, of course. Next, let's talk about computational cost. During my experiments, I noticed that the model I described here required a large amount of GPU memory, actually. Because I had only 1 GPU on my computer, I often encountered memory shortage when stacking layers in deep learning models. So actually, I needed to do many experiments. This seems to be a problem because of the CNN model, CNN architectures, on sample model on S2 because we need to run the CNN model for each order curve, right? So as the number of sample point increases, the GPU memory requirement also increases. Yeah, so I had to try many various approaches to make the model lightweight. Lastly, let's discuss the persistent homology. Persistent homology is a methodology that effectively captures topological change in a filtration using techniques such as persistent barcode or persistent landscape. And since each Euler curve is also generated from a filtration for each direction, so I think that the usage of persistent homology or persistent cohomology could be helpful in various ways. Yeah, that's all I have today, and I hope my presentation has been helpful, and thank you very much for your attention.